All right, does somebody want to type into chat, or if you would like to unmute yourself, what would be 2 plus 3i times 4 plus I simplified?
Is it a polynomial?
So, right, we would be kind of doing it like two polynomials, right? So you got a FOIL.
You want me to
So
type
we
it?
have.
You want me to type it?
You could say it.
It's kind of echoey. I got 3i squared plus 18i plus 8.
3i squared plus what I?
14i.
14i plus 8. Okay. And then in chat, we have 5 plus 14i. So you're all right. Just be careful. So remember, anytime we see I squared, what can we replace that with? What do we know I squared is equal to?
-1.
-1. Okay. So this 3i squared would become -3. So -3 plus 8, and then we have the 14i. The -3 plus 8 gets us the 5 plus 14i. Okay, so good. So you would be correct with this, Barbara. Just make sure that you continue to simplify because the I squared gives us -1.
So every time I squared, we always simplify it?
Correct, yeah.
Okay.
All right. Good. All right. So one part of I don't remember if we saw this last week or 2 weeks ago or whenever the last time we talked about this was, we can multiply two complex numbers together and we can end up with either just an imaginary number or we can end up with just a real number. Now there's a special property of complex numbers, and I just gave it away. Okay. That's called a complex conjugate. Now what a complex conjugate does is it kind of helps us remove an imaginary part. Now this is only used in specific parts. Last year in Algebra 2, when you guys were solving quadratics, and you used that famous quadratic formula, right? You ended up sometimes with imaginary answers, right? When you had a negative number underneath this radical. Now, it's already built into the quadratic formula, this plus or minus. This gives you complex conjugate solutions, all right? So, right, so if we have some complex number, a plus bi, then what we do is we change the sign of the imaginary part, and that's called the complex conjugate. Okay. And like I said before, what's nice is anytime we multiply complex conjugates, it'll give us a real number. So quickly, I'm gonna go over an example of doing that. and then we're going to move into why we do this. All right, so it's a lot to write out, so I'm just going to abbreviate complex conjugate as CC for now. All right, so we're going to take a look at a complex number 4 plus 3i. All right, so 4 plus 3i, our imaginary part here is positive. So the complex conjugate, I'm just going to put it next to it. Right, we keep the same constants. Right, the 4 is still a 4, the 3 is still a 3, but we just change that from positive to negative. Okay, and if we started off with negative, then we would just change the negative to positive. So when we go ahead and we FOIL this, all right, well, 4 times 4 is 16. 4 times negative 3i is negative 12i. Positive 3i times 4 is positive 12i. And then the outside, we get negative 9i squared. So what happens here is, the reason we chose the conjugate is these imaginary terms in the middle will eliminate each other. Okay, and we specifically chose the conjugate for that reason. Okay, and again, right, here we see an I squared. So anytime the I squared is attached to something, we're going to change its sign. So that 16 is staying 16. And then this becomes positive 9. And then we can just add those together. And we get a real number, 25. All right, so that's, we use the conjugate of our original complex number to manipulate it to get solely a real number, okay, just the real part. All right, so other than the fact that actually we'll get to that later. One of the main reasons we use this is to simplify a complex quotient. So let's take a look. All right, so here we have a complex quotient, 2 plus 3i over 4 minus 2i. Now, in math, anytime we have a fraction, anytime we have a quotient, we have some strict rules for what's allowed to go in the denominator. In reality, we only want positive whole numbers in the denominator. If it was anything other than a positive whole number in the denominator, it doesn't really make sense, okay? You can't divide by an imaginary number, okay? That doesn't, conceptually, that doesn't make any sense, okay? In algebra, you've seen we don't like square roots in the denominator, right? We go through steps to get rid of something like, 2 over root 2. Right? That's something you might see if you're talking about the unit circle, right? Again, we don't like the square root of 2 in the denominator. You can't really divide by an irrational number, right? This doesn't make sense. So what we do here, right, is we multiply both the top and the bottom by the square root of 2, and we can get a simplified. Right, so the value, the actual numerical value of 2 over the square root of 2 is the same thing as just the square root of 2, right? And this is a lot nicer to look at, the square root of 2, than 2 over the square root of 2. Okay, this makes a lot more sense. This is a lot cleaner than this whole expression. So the same holds true for imaginary numbers. We don't like imaginary numbers in the denominator. So you may end up with a situation where you have something like 2 plus 3i over 4 minus 2i. So to simplify this, okay, we want to get the denominator to be a whole number, a real number. So what we're going to do is we're going to multiply the bottom by the conjugate. But as always in math, we have to keep things even, right? So I can't just multiply the denominator by the conjugate. I also have to multiply the numerator by the conjugate, right? Because when I multiply by something over itself, technically I'm multiplying by 1, right? And I'm not changing anything when I multiply by 1, right? That's going, again, back into algebra, right? So now it's a little bit of work, so just be careful, right? But you have to FOIL twice, right? You're going to FOIL your numerator, and now your numerator will still have an imaginary part. That's okay, right? That's expected. But it should work out where your denominator is no longer complex and you only have a real number. All right, so I'm going to do the work down here. So I'm going to do the numerator first. So I have 2 plus 3i times 4 plus 2i. All right, 2 times 4 is 8. 2 times 2i is 4i. 3i times 4 is 12i. Now, again, be careful here. 3i times 2i is 6i squared. Right? So we know that this is going to be negative 6. So we have the 8 minus 6. That's going to get us 2. And then we combine our imaginary part, and we get 16i. So my new numerator is going to be 2 plus 16i. Okay, and that you're just going to do like we did for the warm-up. All right, you're just foiling, and you're going to come up with another complex number. It may so happen where you get, either just an imaginary part or just a real part. But for the most part, you'll come up with a complex number. Now, in the denominator, again, it should work out where it just ends up being real. 4 times 4 is 16. Positive 8i. Negative 8i. That's good because those will eliminate. And then a negative 4i squared. Again, we see that I squared telling us we're going to change the sign, so this becomes plus 4. So we have 16 plus 4, and there is our nice real number, 20. Okay, so we started with 2 plus 3i over 4 minus 2i. We multiplied numerator and denominator by the complex conjugate of the denominator. And we have 2 plus 16i over 20. Now, they may ask you to go further because remember, standard form for complex numbers is a plus bi. So if you see something like this, you would just kind of distribute that divided by 20 to both. So you would have 2 over 20 plus 16i over 20. And then you would just simplify any fractions, right? So 2 over 20 would become 1 over 10. And then the 16 over 20, we can divide both of those by 4. So that would become 4 over 5i. All right, any questions there?
Can we do some practice problems?
Yeah, we'll do one more. All right, so we're going to do 3 minus 2i over 3 plus 2i. So first, I'm just going to rewrite it so we got some room. Okay, so your steps are, well, first, what's in the denominator? We have 3 plus 2i. What is going to be the conjugate of 3 plus 2i? Who can tell me?
3 minus 2i.
3 minus 2i. 3 minus 2i. Good. All right, so you put that in the denominator times 3 minus 2i, and you put it in the numerator. Okay, it just so happens it's the same thing as the numerator, but that just, that's coincidence or whatever. All right, so your next step is you're going to FOIL these separately. So I'm going to separate them down here. So here we have 3 minus 2i times 3 minus 2i. And then we'll do 3 plus 2i, 3 minus 2i. So in reality, this is where most of your work's coming in, when you have to FOIL the top and FOIL the bottom. Okay, so again, all I did was I just separated them so we can work on them separately. All right, so we're going to FOIL. 3 times 3 is 9. 3 times negative 2i is negative 6i. Negative 2i times 3, again, is negative 6i. Negative 2i times negative 2i is positive 4i squared. This I squared is going to change my positive 4 to negative 4. So for the real part, we have 9 minus 4, which is 5. Negative 6i plus negative 6i, or negative 6i minus 6i, is negative 12i. Just be careful there with your signs. All right, so we have the new numerator. 5 minus 12i. And so we FOILed the numerator and we simplified that. Now for the denominator, again, we should end up with just a real number. 3 times 3 is 9. Outer, we get negative 6i. Inner, we get positive 6i. And then with the last, I get minus 4i squared. Our outer and our inner terms eliminate each other. 6i minus 6i. This positive 4i squared, negative 4i squared becomes plus 4. 9 plus 4 is just 13. Okay, so again, technically this isn't in standard form, right? So you're just going to separate it with fractions. So your real part is going to be 5 over 13. You keep whatever sign is there, that's a minus. 12 over 13i. All right. Any questions?
Personally, no.
All right. So you guys are going to practice this, just this. I'll give you one, maybe two questions where you have to do this today.